So now that we've kind of covered that, do these two things look familiar to you? I find that fewer people know about the left one than the right one. So raise your hand if you remember what the right one is. Oh, that's fewer than I thought. So PV equals nRT isn't ringing any bells? PivNert? You probably would have had something like a problem where you were given the volume of a gas and maybe its temperature and asked to find the pressure. And pressure would have been measured in what? Do you guys remember what you measured pressure in? So PSI is a measure. You probably didn't use that in your chemistry class, but you probably use that as a measure when you like inflate your tires. Pounds per square inch. What might you have used in chemistry? Pascals. That would be the unit that I probably used. There's two others that you might have used. I used atmospheres once in a while. And then sometimes I never used it, but some people in their chemistry class use millimeters of mercury. But I was never familiar with that scale myself, and so I never taught it in class. What'd you measure V in? Probably liters. We're not going to use liters in here. We're going to try and stick to things that have meters, kilograms, and seconds. You don't know this, but Pascal is measured in meters, kilograms, and seconds. I never told my students what it was. Did anybody tell you guys what it is? Well, somebody in the room helped us out already because they said PSI, and that kind of helps. PSI is pounds per square inch. So that's pounds over inch squared. The unit of pressure is force against an area. That's what pressure is. So you've learned about force already. Pascal is going to be the metric equivalent of pounds per square inch. It's just name for a guy, Pascal. But the measurement is newtons per meter squared. Now, the V, volume, you said liters. What if I wanted to use meters, kilograms, and seconds? Can you tell me a way of measuring volume using those? I was afraid of that. See, and this scares me. Go ahead.
Could you do meters cubed?
You could do meters cubed, yeah. No longer scared, yeah. So, you guys understand a cubic meter? All right. Now, here's where I want to just dive off a little bit. This side, do you remember what any of this is? I mean, some of these you could probably come up with. Yeah, change in temperature there. What do you think? Mass, sure. This one, I don't know if you'll remember it or not. So specific heat is the amount of heat required to change that material's temperature. For water, the specific heat is 1. We defined the whole thing based on water. Now, when I say 1, I mean in terms of calories, it would be 1. In terms of joules, it would have been 4.19. Now, still working this out here, do you know what you were doing when you multiplied all those things together? Yeah. Not quite, because to change state, you would also have to have something like this, where this is the latent heat of fusion or the latent heat of vaporization. Do you guys remember that from chemistry? So a change of state doesn't change the temperature. You're adding energy to the system, but the temperature doesn't change, but the state of the material changes. Go ahead.
Isn't Q supposed to represent the heat or joules required to change it?
So Q represents the energy required or the energy you get from this change. So if I drop the temperature of something, I release that amount of energy. If I want to increase the temperature of something, I need to provide that amount of energy. Q represents the heat energy. You see, in chemistry, the word heat means the flow of energy from one thing to another in order to change its temperature or change its state. Heat isn't something you have, which is why this stupid word, specific heat capacity, kind of sucks, because it suggests you could have heat, and that's not true. Heat is the flow of energy. So all of these would have equaled something, well, in your class, which meant joules, but it was talking about temperature. Here's the thing that's weird. This is why I want to get to this. This is actually an energy statement too. You were never taught this, and this isn't your fault. You weren't ready for it. So let's see if I can ring some bells a little bit here. Imagine I have a cylinder, and in that cylinder I have a kind of a movable piston or lid. So I can put gas in this section, and if the gas expands, it can push downwards on this, I don't know what you want to call it, this lid that's on the inside. I could turn it around and make the lid on the top if that makes this better, but I think the lid on the bottom will work better for my example. Is that okay? If I, put fire all around this portion here, if those are fires, I put fire all around it, the gas will get hot. And if the gas gets hot, what's it going to do? So I'm making this side bigger, and when I do so, the pressure of the gas increases. And you guys remember Boyle's law and Charles' law, Gay-Lussac's law and all that. So as the pressure increases, the motion of the particles is getting faster because the temperature is getting faster. That means they're hitting the walls more. That's the increase in pressure, and if they increase the pressure, I could likely cause the volume to expand and push the piston downwards. Does that seem familiar to you guys? So one way to cause this temperature to change, as opposed to heating it from the outside, would be to put something in there. So say I connect a tube to the top of this cylinder, and I inject something flammable into the cylinder. So I could just put gasoline in there, right? So if I sprinkle gasoline in there, I could ignite it, and the gasoline would explode inside the cylinder. What it would really do is it would change its temperature radically, right? Increasing the temperature dramatically. That would create a huge amount of pressure, and that would push down on that piston. If I connect that piston then to something that, like a pedal, like on a bicycle pedal, you could push down on the bicycle pedal. You guys know what a bicycle looks like, right? Push down on the pedal, the bicycle thing goes around. Now, if I have one on the other side that could push down on that pedal, then when one's up, it can be pushed down, and the other one is being brought up by the action of the pedal on the other side, right? So while the other side pedal is being pushed downwards, I could push this back up. I could open up, say, another tube, get all that spent fuel out of there, right? And then repeat the process by bringing in some more gasoline and igniting it. This is how a basic gasoline engine works. Now, a two-stroke engine does it like this. A four-stroke engine has an extra couple strokes in there to use the momentum of the engine to bring in the new gas and expel the old gas. But it's a simple idea, and of course, it powers almost all of your cars and has for about 100 years. The internal combustion engine is this formula. What's amazing about it is what you don't realize is a statement of how energy actually works. The right side of this is all about temperature, igniting the gas. The left side is about pushing on the piston. Look at these two units here. It's newtons times meters squared times meters cubed. What's that going to give you? When I multiply that out and clean up those units, this will be newtons times meters. This is why I always found it weird that they use joules in chemistry. A Newton meter is a joule. That is the definition of a joule. The definition of a joule is physical, very physical. It's a force and a displacement. In fact, that's the definition of work. The pressure and change in volume is this calculation. They are the same. Pressure represents the force. Volume is the change in position. Now, this was a calculation of work in chemistry. You were never told that because you weren't ready for it. We're not going to use pressure and volume in this class. We're going to use force and displacement. But this is the statement of work. Now, it's just an equation. And because it's just an equation, I need you to realize that you have lots of equations. Knowing equations doesn't tell you very much. So let's have a few statements added to this. So first, work is anytime a force is used to cause a displacement. That's what this is about. The force has to have a component in the direction of motion. So you can have lots of forces acting on an object, but only forces that have components in the direction of motion do work. So I can say that slower, but this is our definition of work. If an object is experiencing lots of forces, any forces that are in the direction of the displacement are doing work. Let me say that again. We can have lots of forces acting on an object, but only forces that are in the direction of the displacement are doing work. So if you're doing push-ups, you're doing work, right? Because your body's being displaced. But there's lots of forces that are acting on you while that is happening. Not all of them do work. That's why this is here. And this is just something to help you out, but I want you to be understanding that this is a vector, generally. This cosine represents the angle between these two vectors. So cosine is the adjacent side. So when you do this product, what you're doing is you're finding how much of the force is in the direction of motion. You find that out by multiplying by the cosine of the angle between them. So, real simple. If I have a box and I pull it with a force this direction, and the box slides across the floor, I'll answer your question in a minute. The displacement will be along this dotted line. All right, that'll be the direction of the displacement. So if this force, if we wanted to find out how much work is being done by this force, then I would need the size of this force, I would need the size of the displacement, but I would also need this angle to tell us how much of the force is in the direction of the displacement. We're going to do an example in just a minute, but I want to just talk a few more things about this calculation. What's your question?
I was just saying that, didn't we do this in kinematics, basically?
Very, very like what we did in kinematics, but we're going to develop something from this that we didn't develop in kinematics. Briefly, remember forces in newtons, delta X is in meters. So this is a joule, which is a Newton meter. I hate doing this, but I have to really make sure we understand. Newton is kilograms, meters per second squared, times meters. So the actual unit of a joule is a kilogram meter squared per second squared. Remember when I wrote all those on the board that one day and said these are all the different units for physics? And I just laughed. I said every one of these means something different. I don't know that I see all of that in there. I see this in there. That makes sense because that's what it's doing, right? A force used for displacement. I don't know that I see kilograms and meters and seconds and all that in there. That seems harder to see. But that's the actual unit of what a joule is. You see now why I find that weird that you did that in chemistry and didn't use calories. Since calories were all about water, that seemed like that'd be the right thing to use, but not so much. Now, having an equation isn't the end all. You have to understand what work is about. So let me just take a few minutes to give you some definition about what work is actually about. We have been talking a lot about some foundational topics, forces, kinematics, stuff like that. Work is how you change something's energy. Work is what you have to do to change something's energy. This is true in chemistry, biology, physics, any science. Energy is changed through work. In fact, I always say that work is the method by which you physically change something's energy. I'm not replacing conduction, convection, and radiation. That's how you transfer heat energy. But this is how you transfer energy physically, through contact. So you push on something, you can transfer energy. But we don't get a new rule and ignore the old rules. There are still old rules there. If the forces that you're adding together balance, then the object's velocity doesn't change. That's still true. Work can be done, but that doesn't mean that you're necessarily changing the object's velocity. Of course, if the forces you are using are unbalanced, then you're also changing the velocity of the object. You can be doing work and changing something's velocity at the same time. But also, we don't forget the fact that there are always two forces. You apply a force on an object, and that object applies a force on you. So whenever you're doing work on something, it's also doing work on you. We often call this the agent and object. The agent does work on the object, but the object is also doing work on the agent. This is the flow of energy. If I do positive work on an object, I am increasing its energy. Understand, work is not a vector. So positive and negative mean something different here. Positive work is an increase to the overall energy of the object. Negative work is a decrease to the energy of the object. It's not up and down, left or right anymore. Okay, I'm saying it again, work is a scalar. Positive work represents increases in energy to the object. Negative work means decreases in energy to the object. Work is not a vector, it's a scalar. So if you do positive work on an object, that object is doing negative work on you. Anybody go to the gym? I'm looking around this room and I'm not sure all of you do. But let's say that all of you do regularly, because you're clearly showing gains out there. You understand that you are really doing this, right? Every single machine you use is a clear indicator of work being done. I mean, have you, no matter how, whether it's free weights or if you're using machines, have you noticed that every machine is the same in the end? That little stack of weights gets lifted. I mean, that's you doing work against gravity, right? You're pushing some lever, but eventually the weights went up. Or maybe you walk to the free weight section, you just grab the weights, but if you're doing any kind of activity, you're lifting against gravity. That's how much all of your workouts do, unless you're doing body work, or I'm sorry, you're doing body manipulation exercises, using your own body weight. That just means you're moving your body against gravity, right? You hang yourself or you push yourself up or some way so you can lift your body against gravity. Now, I'm bringing this up because we need to kind of talk about what does this mean mathematically, because you know our whole goal here is to mathematically model the universe. So let's see, if I have a 15 kilogram box and I want to lift it 2 meters into the air. So we're talking about like a dumbbell that you're going to lift or deadlift from the ground. What's the minimum force necessary to lift this? Nobody? Oh. Yes, sir?
What
Well, if I want just to go up at a constant velocity, I think 150 will be enough, right? A little bit more at the beginning just to get it started, but then 150 to get it up there, right? If you've done any lifting of weights, you know that the goal is to maintain a nice, consistent motion the whole time, right? You don't really want to accelerate the weights up there. You just need to get them up there in a controlled manner, right? So you're right. The minimum force necessary would be 150 newtons. So the work would be 150 times 2 times the cosine of 0 degrees, right? We're pushing up on the box, and the box is going up. This would be 300 joules.